Okay, we're continuing example 16.3 from the textbook, in which we're designing a timber beam. It's part of a system of joists. And what we've done so far is we've taken the floor loads, which are spread out in pounds per square foot. We've multiplied it by the tributary width of the beams, which is equal to the spacing of the beams. And we have found the loads here in terms of pounds per linear foot. The span of our joist is 16 feet long. And the problem statement tells us that we are using hem fir. That's the species of timber that we are using. So, and it also tells us it is S4S. So what does S4S mean? Well, if we look at a cross-section of a piece of lumber, what that means is on all four sides, top, bottom, left, and right, all four sides have been planed. So they're nice and smooth. The lumber is first just rough sawn in a sawmill, and then planed to get a nice smooth surface. Most lumber used in construction is S4S, but it doesn't necessarily have to be. You can purchase lumber that is perhaps surfaced on only one side, or two, or three, or maybe it's completely rough sawn. That's going to affect the dimensions, which will affect the strength of the timber, so that's why it's important to know that it is S4S. We also need to know some other properties of hem fir, such as its allowable bending stress. So we'll have to refer to Appendix F. And we can see that hem fir has an F sub B, an allowable bending stress of 1,000 psi. So the loads that timber resists are typically in the magnitude of pounds rather than kips. Wood, although it has a good strength to weight ratio, is not as strong as steel, which uses kips. And we'll also need to know the strength, the allowable stress with respect to shear. That's 150. You can see that's quite a bit less. As I talked about in the last video, wood is anisotropic. Its strength greatly depends on how the load is being applied with respect to the direction of the grain of the wood. And we should also write down, while we're looking in this appendix, the modulus of elasticity. The modulus of elasticity of hem fir is 1400 KSI, which would be 1.4 million, 1,400,000 PSI. Okay, so now that we know that information, we can start to look at our one individual joist, which has 53.3 pounds per foot live load and 20 pounds per foot dead load, and calculate what the moment would be so that we can know what section modulus we're going to need. So let's begin that calculation down here. In terms of the section modulus, I'm going to combine the two loads together. So the total load W is going to be 53.3 plus 20 equals 73.3 pounds per foot. We have a simply supported beam with a uniformly distributed load. The formula from Appendix H tells us that the maximum moment for that situation is WL squared over 8. So our W is 73.3 pounds per foot. multiplied by a span length of 16 feet squared divided by 8. And that is equal to 2,345.6, and that is going to be pound feet. So we would like to change our units of length from foot to inch. So we convert feet to inches. For every 1 foot, there are 12 inches. So we're going to multiply that by 12, and that is equal to times 12 equals 28,147 pound inches. So that's the moment that's being applied to these joists by the floor load. So now we can determine what type of section modulus we need to resist that. Section modulus is equal to the moment divided by the allowable bending stress. So if our moment is 28,147 pound inches, and our allowable bending stress, see up here, we wrote down was 1,000 psi, then this will give us a required section modulus of 28.147 inches to the third. So now we want to look up timber size that we can use that will provide a section modulus that is large enough. So joists are typically dimensioned lumber that stand up on their end that are nominally 2 inches in width. So 2x8s, 2x10s, 2x12s, these are types of lumber that are typically used as joists. So if we go to Appendix E to look at the properties of structural timber, and we look at the category of 2x, starting with a 2x4, going all the way up to a 2x18, and we look at that last column on the right for section modulus, it looks like a 2x12 will provide us a section modulus of 31.6, which of course is greater than 28.147. So it looks like this will be good for stress. Now we may need to take into consideration the self-weight. Occasionally the problem statement may tell you that you may neglect the self-weight, but if it doesn't specifically tell you that, then you should always take that into consideration. As I said before, wood has a pretty good strength-to-weight ratio, so the self-weight of timber usually doesn't make a big difference like it would in concrete, but it is something we should check out nonetheless. A 2x12 weight is 4.68 pounds per foot, and that comes from the same appendix where I found the section modulus for a 2x12. So it would be a good idea to calculate how much additional section modulus we need to accommodate this self-weight. First we have to find the moment. The moment is WL squared over 8, so that's going to be 4.68 times our span length of 16 feet divided by 8, and so that is equal to, that's approximately 150 pound feet. Okay, so I'm going to need to convert that. So the moment from the self-weight was equal to 150 pound-feet. So if I convert that to pound-inches, every 1 foot, there are 12 inches. And so 150 times 12 is 1,800 pound-inches. And so the additional section modulus needed because of the self-weight would be 1,800 divided by the allowable bending stress of 1,000. So that's only an additional 1.8. So if I add that back into the section modulus that's required due to the floor loading, I'm looking at about, let's just round that up to 28.2 plus 1.8 gives me a total of 30. So again, this is for the self-weight. This is from the floor load. And this then would be the total amount of section modulus required, 30. And if we go the 2x12, we will be providing 31.6. So a 2x12 will be adequate to resist bending stresses. I still have a few minutes left before I reach my 15-minute maximum, but I think this is a good place to stop. We have chosen our timber beam based on bending stress. What remains now is to check deflection and shear stress. So we'll do those two things in the next video.